Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the BSc students of Applied Electronics. In continuation with what we have been seeing in the last lecture, we will see the other aspects of the vector atom model. The name vector atom model was given because of the fact that the angular momentum of the electron, the orbital angular momentum as well as the spin momentum are all vectors. Momentum is a vector, and again the resultant angular momentum also is a vector. And so then these two vectors, that is the orbital angular momentum and the spin angular momentum, ought to be vectorially added. So the contents of this lecture are given here: intrinsic magnetic moment, resultant angular momentum, quantum numbers associated with the vector atom model, total magnetic quantum number. As I told you, in the Bohr atom model, we come across only one quantum number, namely the principal quantum number, whereas in the Sommerfeld model, we had 2 quantum numbers. One is the principal quantum number, the other is the azimuthal quantum number k. In the vector atom model, we talked about space quantization. Unlike the case of Bohr atom model, where the electron can revolve in all possible orbits, you have the circular orbits, but the orientation can be anything. But here that orientation is restricted. That is what we call as space quantization. By space quantization, what we mean is the electron orbits are oriented only in certain planes. You have got a plane here, another plane here. Only selected orientations are allowed, or the angle theta that the plane subtends with respect to an applied magnetic field, that angle theta will have only selected values. Therefore, we talk of L cos theta, the cos theta, PL cos theta or L cos theta, that is the angular momentum, the projection, right, the PL cos theta. So, you write ML is equal to PL cos theta and so on. So, the theta is restricted, and that we call as the magnetic orbital quantum number ML and the magnetic spin quantum number. So, we come across more number of quantum numbers in the vector atom model, and we talked about apart from space quantization, the 2 Dutch scientists who came, who talked about the spin of the electron like the mother earth revolving around the sun. Not only it is revolving, it is also spinning. The kind of spin associated with the earth should also be attached to the electron. The electron will be spinning either along this direction or along this direction. Therefore, along with the spin, there will be a spin magnetic moment. Mu s refers to spin magnetic moment, and if s is equal to half, ms, the magnetic spin quantum number will have 2 values, namely +1 and minus 1. So, spin can be either up, the applied field is like this, the spin can be up or down. So, that is the spin up and spin down. So, ms will be plus half or minus half, s is equal to half, right. The spin quantum number will have a value half. By saying that the electron has got a spin half, it means, as I told you in the last lecture, the spin angular momentum of the electron is half h bar, right. So, by telling that the electron is having spin half, you should not be blinking. The meaning of it is the spin angular momentum is equal to half h bar. Okay. Therefore, apart from angular momentum, there will be associated magnetic moment. When you apply a magnetic field, there will be, for S, there will be two ms values, ms is equal to plus half and ms is equal to minus half. These magnetic spin quantum numbers will come into the picture when you are going to talk about the number of electrons you can have in the K shell, L shell and so on. That we will be taking up in the lecture to come. Here I would like to say the spin can be up or down. Okay. That is what, so it may be ms will be half h cross by 2 or minus half h cross by 2. Therefore, we are talking about electron spin. So, the spin angular momentum will be ms into h bar. I will like to tell you that we talked about orbital momentum. The orbital momentum will be PL will be equal to LH cross. Similarly, the spin angular momentum PS will be SH cross. SH cross means S is half, right. PS can have two orientations. So, PS will be, so or the ms will be, will have 2s plus orientation. Now, what are the quantum numbers you come across? In the vector atom model, you come across the quantum number n, the principal quantum number. It will take values from L is equal to 1 to n. So, L is equal to 1, n is equal to 1 means that is the K shell. Then you come across the orbital quantum number. So, n and then L. Orbital quantum number will take values from 0, 1, 2, etc. The spin quantum number will take a value half. So, how many? N, L, S. Now, L and S can be coupled. The momentum, the spin angular momentum, PL will be equal to LH cross, PS will be equal to SH cross. Then the L will have 2L plus 1 ML values. For every L value, the magnetic orbital quantum number will have 2L plus 1 values that I told you in the last lecture. Similarly, MS will have 2S plus 1 orientations, 2S plus 1 values. When S is half, 2S plus 1 will be 2 into half, that is 1 plus 1, 2. So, when S is half, MS will be plus half or minus half. Okay. When ML is 1, when L is 1, ML will take 3 values. What are the 3 values? The integral values. When L is 1, ML will take how many values? 2L plus 1 values. 2L plus 1 means what? L is 1 means 2 into 1 plus 1, 3 values, namely minus 1, 0 plus 1. These are the ML values. Similarly, now if S is half, MS will take 2S plus 1, that means equal to 2 values, either plus half or minus half. That is what I am showing here. MS will take 2 values, plus half and minus half. That means, when you apply a magnetic field, it is called the magnetic spin quantum number. When you apply a magnetic field, the electron will orient either along the field direction, the applied magnetic field direction, or opposite to that is the applied magnetic field direction. So, if it is aligning itself along the field direction, then MS will be equal to plus half. If it is the other case, MS will be equal to minus half. Okay. So, it is a parallel orientation, spin up, anti-parallel, spin down. So, the intrinsic magnetic moment. What is the intrinsic magnetic moment? The electron is having a spin which is equal to half. It is called an intrinsic angular momentum. Whenever we are talking about electron, let us not go into origin. There is the experiments like Stern and Gerlach experiment. They show, many experiments show that the electron, apart from the orbital motion, the momentum due to orbital motion is LH cross. Apart from the orbital momentum, it should have a spin momentum that will be equal to half h cross, and every electron will have a spin motion. So, when you spin angular momentum, there should be a spin magnetic moment. The magnetic moment mu s of a spinning electron is given by an expression of this kind, where you have mu suffix s. Mu refers to the magnetic moment, s refers to spin. The spin magnetic moment will be 2 times E by 2 m into P s, and this 2 comes because of the fact that G, that is the, what is G? G is the Landé splitting factor that we spoke in the last lecture. I told you in the case of orbital motion, the Landé splitting factor is 1, whereas in the case of spin motion, the Landé splitting factor will be 2. Therefore, you have mu s is 2 times E by 2 m into h cross by 2, and you know h cross is the unit of angular momentum. So, this becomes now E h cross by 2 m. So, that will be this E h cross by 2 m is called 1 Bohr magneton. You know E h cross by 2 m or 2 m c depending upon the SI units, or depending upon the unit you choose, either you have E h cross by 2 m c or 2 m. So, this E h cross by 2 m is known as 1 Bohr magneton. What is Bohr magneton? It is a unit of magnetic moment. I told you nuclear magneton also. In the case of nucleus, you have the nucleons inside the nucleus, and the mass of the nucleon will come into the denominator. Here m is the mass of the electron. Therefore, the spin magnetic moment mu s will be E h cross by 2 m, where m is the mass of the electron, and this mu b that you have got here, which will be equal to E h cross by 2 m, that is known as the 1 Bohr magneton. As I told you just now, when I started with my lectures, it is called a vector atom model, because the angular momentum, the orbital angular momentum, the spin momentum, the spin angular momentum, as well as the orbital angular momentum, namely PL and PS, they can be vectorially added. When L and S are added, that will result in resultant angular momentum. When what is resultant means? The resultant of orbital angular momentum and the spin momentum. Therefore, the orbital angular momentum and the spin angular momentum, both of them can be vectorially added. That gives rise to what is called P suffix j, where j is called a resultant angular momentum quantum number. What is j? J is the resultant of L and S. L is the orbital momentum quantum number, S is the spin quantum number, PL is the magnitude of the orbital angular momentum, PS is the magnitude of the spin angular momentum. The sum of these two, that the resultant of these two, is Pj. So, j is the resultant angular momentum quantum number, and Pj is the resultant angular momentum. So, when you take an electron, it will have orbital momentum, that is PL, the spin momentum PS. These two can be vectorially added. The vector addition gives Pj. Pj will be j times h cross, and this j is called the total angular momentum quantum number, or it is the resultant angular momentum quantum number, or it is the total angular momentum quantum number, because the total angular momentum means both the addition of orbital angular momentum and the spin momentum. Therefore, your resultant angular momentum will be either, you can write j h cross that I had here, either L and S have the same orientation, L and S oriented the same direction, then you have L h cross plus h cross. Your j h cross, that is the resultant momentum that you have got here due to the orbital part and the spin part. If PL and PS or the vectors are the same direction, then they are to be added in this fashion. If S, as I told you, or MS, as I told you, will have two values, either spin up or spin down. So, depending upon the spin orientation, you can have either j h cross is equal to L h cross plus S h cross, or j h cross will be L h cross minus S h cross, right. This is the two vectors L and S are oppositely directed. In the first case, S is having up spin, the spin is in the upward direction, this is the magnetic field direction, the spin is in the upward direction. The second case, spin is in the downward direction. All the vectors have common factor h bar. You know, the momentum is given in terms of h bar, it is a unit of angular momentum. Therefore, you can write, you do not worry about your h bar, it is common. Therefore, you can write J is equal to L plus S. The resultant momentum J or the resultant J will be L plus S or L minus S. Let us have a break at this point. Welcome back to the break. So far in the vector atom model, I have been telling you about the quantum numbers n. What is n? N is the principal quantum number, L is the orbital quantum number, S is the spin quantum number. So, S will have a value half, whereas ml, what is ml? ml is the projection of L. You know, when you apply a magnetic field, if you call L as the orbital quantum number and ml will be called the magnetic orbital quantum number. When you apply a magnetic field, then when you have a applied magnetic field, so for a given L value, namely 1, ml will have how many values? 2L plus 1 values. If S is half, whatever be the S value, whatever S value you got, ms will have 2s plus 1 values. So, L will have the projection ml, S will have projection ms, ml is called the magnetic orbital quantum number and ms is called the magnetic spin quantum number. And then you got J also. What is J? J is the resultant of L and S, right. This is what I am showing here. J is the summation of L and S. It can have either L plus S or L minus S. Now, from J, then after J you can have mj. For L you got a projection ml, for S you got a projection ms. Similarly, for J you will have the projection mj. For instance, now let me take L equal to 1, right. S is half, 1 plus half will be 3 by 2, J will be 3 by 2. So, mj will have 2j plus 1 values. 2j means what? It is 3 by 2. So, 2 into 3 by 2, that is 3 plus 1, 4 values, right. So, mj will have 2j plus 1 values, ml will have 2l plus 1, ms will have 2s plus 1, mj will have 2j plus 1 values. Okay. So, this is the resultant angular momentum due to orbital motion p suffix l. This is with regard to spinning, right. The spin momentum Ps is shown here. These two are coupled vectorially, that is what I showed in the previous slide. So, when you have J equal to, what is J? J is the resultant of L and S. You have got L vector here, S is half, the resultant of these two will be given by J. Supposing S is minus half, S is acting opposite to that of your L, L is here, the resultant J will be L minus half, right. As I showed earlier, J is equal to either L plus S or L minus S depending upon the spin orientation. I show here the spin orientation is in this direction, here it is in the opposite direction. So, the resultant in this case is L plus S, in this case it is L minus S. Okay. So, that is the resultant momentum, resultant angular momentum. Partly it comes from the orbital momentum coming from the orbital motion, the other is the spin momentum. Okay. Then for a electron, you know, S is equal to half, hence J can take the two values, namely J is equal to 1 plus half, or you can have L may be equal to 1. Okay. So, L plus half or L minus half. supposing you take the state L is equal to 0. What is L is equal to 0? That we will call a S state. By now, even in high school you write 1s2 for the electrons in the helium atom, you write the electronic configuration 1s2. So, L is equal to 0 is called a S state, that will come, I will come to that later. J can have L is 0 means what? 0 here. So, 0 here, J will be plus of, here L is 0 minus of. So, J will have values like plus of or minus of. If L is 1, then what happens? 1 plus half will be 3 by 2 or 1 minus half will be half. Therefore, for a given L value, right, L plus half or L minus half, they are the two possible J values. So, J or Pj is the resultant momentum, right, resultant angular momentum. It is sum of the orbital and the spin momenta, both of them are coupled together. So, the quantum number J will have values like 3 by 2 or half. For a given J value, Mj will have 2J plus 1 orientations. So, in this model, a quantum number is assigned to each of the component parts. The numerical value of the quantum number may be thought of as the length of the vector. The additions of the components are carried out as per the rules of vector analysis. A straight line whose direction is parallel to the axis of rotation and whose length is proportional to the magnitude of the momentum represents the orbital angular momentum as shown here. This is the orbital angular momentum, right. You have the L vector, the magnitude shows the orbital angular momentum. Here again the orbital angular momentum, and this is the spin momentum. Okay. The resultant momentum is shown here. Now, this is what I have stated here. Then now we will pass on to the quantum numbers associated with the vector atom model. This part is very, very important for the simple reason we are to find how many electrons you can have in the K shell. You take the whole of periodic table. You look at the periodic table as was made by Mendeleev, the Russian chemist. The Mendeleev, one of the top 10 discoveries of the world, the periodic table. Now, how do you find the number of electrons in lithium? Number of electrons means how are the electrons arranged in lithium or sodium or potassium or platinum, gold, how electrons are arranged. Whether supposing you take 11 electrons in sodium, will you have all the 11 in the first shell? You have got the K shell, the L shell, and then so the question is how many electrons you are going to have in the first shell, how many are going to have the second shell, how many are going to have the third shell. Not only in the shell, I will be talking about sub shells. For the first shell, the main shell and the sub shell are one and the same. For the second shell, first one is the K shell, the second is the L shell. For the L shell, there will be 2 sub shells. For the third shell, for n equal to 3, there will be 3 sub shells. So, the question that we have in front of us is how many electrons you can have in each and every sub shell, then each and every main shell. You have to sum up all the electrons that you have got in the sub shell to find the total number of electrons in the main shell. Main shell consists of sub shells. Now, those things, the number of electrons you are going to have, the rules governing the number of electrons you are going to have in a main shell or sub shell come from the quantum numbers which are being studied in the vector atom model. The quantum numbers are very important. I will tell you now, unlike the Bohr atom model, we have only one quantum number. We had 2 in the Sommerfeld model. Here in the vector atom model, you are going to come across as many as 7 quantum numbers, which I am going to discuss now. At present, I am going to talk to you about the 7 quantum numbers that you come across in the vector atom model. The quantum number associated with the electron in a given atom in the absence of a reference field initially are as follows. The principal quantum number, as I told you, n, an electron is characterized by a principal quantum number which describes the quantization of electron energy. It can take only integral values starting from 1 to n. As I told you, 1 equal to n equal to 1 means it is a K shell, 2 means it is L shell, and so on. Okay. Then second is the orbital quantum number L. The shape of the orbit is characterized by L, which may take integral values starting from 0 to n minus 1. If n is 4, L can take values like 0 and 1, 2, 3, right. In the vector atom model, the orbital angular momentum of the electron is given by P L is equal to L h cross. What is the meaning of, suppose I say the electron is having, or electron is being found in the L is equal to 1 state. L is equal to 1 means 1 is here, right. P L is equal to 1 into h cross, that is, the electron is having a orbital angular momentum which will be equal to h cross. So, when I am talking about this kind of P L equal to L h cross, this is according to the quantum theory, but according to quantum mechanics, which I will be dealing with in the time to come, in the lectures to come, one finds that strictly speaking, instead of L h cross, P s goes as, or P L goes as L into L plus 1 into h cross. P L is L into L plus 1 into h cross. Similarly, P s will be S into S plus 1 into h cross. Now, therefore, the things are becoming different. So, it is a common practice to designate the stated different L values as follows. Now, I told you about the different L values. L will take values from 0 to n minus 1. If it is 0, that is called a S state, that is the first subshell. In a given shell, the first subshell, it is designated by the letter S. You know S, P, D, F, these things you have studied in the high school. So, you got a electron in the S state, P state, D state, and so on, right. Okay. Therefore, depending upon the orbital quantum number L is 0 means S state, this is a P state, D state. So, the values of L are given here and they are correspondingly written. And as I told you just now, for similar to P S, P L, for P S you have got S into h bar by 2 pi or S into h cross, that is what you have in according to older quantum theory, but according to quantum mechanics, right, got a quantum mechanical model, P s is more rigorously found as S into S h cross, S into S plus 1 into h cross. So, S is replaced by square root of S into S plus 1 into h cross. So, we have now spoken about the 3 quantum numbers n, L, and S, right, n, L, S. Now, L and S can be coupled, that gives the resultant, namely J, the total quantum number J. I told you, when you apply the magnetic field, we talk of mj. Now, so far we are seeing the 4 quantum numbers n, L, S, J. Then you have to have the applied magnetic field, because applied magnetic field you will have the magnetic orbital quantum number ml, the magnetic spin quantum number ms, and the magnetic resultant quantum number, namely mg. And all these quantum numbers which are to be taken into account, as I told you now, the remaining quantum numbers ought to be seen in detail, then only the number of electrons you can have in any shell or subshell can be understood in a proper manner. Let me now try to summarize from what I spoke to you today. The intrinsic magnetic moment is due to spin of the electron and it is equal to 1 Bohr magneton. The resultant momentum of an electron is the vector sum of orbital and spin momenta, and the 7 quantum numbers which I have been repeatedly telling. I told you, you got n, L, S and J, and I also mentioned about the projections of L, S and J, namely ML, MS, MJ. All these 7 quantum numbers ought to be taken into account to find the number of electrons in a subshell and finally in the main shell. Let me now have the following questions posed to you, namely, give the expression for the orbital momentum and spin momentum of the electron. Question number 2, what is the unit of magnetic moment? The last question, mention the quantum numbers associated with the vector atom model. With this, we come to the end of this lecture, a part of which is to be done in the sense that the other quantum numbers I spoke to you toward the end are to be continued in order to have a proper understanding, or in order to determine the number of electrons you can have, as I told you, in a subshell and main shell. That will be done in the lecture to come. Thank you.